So, in the previous lecture we saw what is the maximum drawing reduction that is allowed. If you go beyond that, remember the material will fracture outside the drawing or the die zone, which is something you do not want. Now, we will understand the same concepts and through this stress strain plot, what exactly or where exactly do we see this maximum strain. So, let us draw the stress strain plot. So, we are looking at maximum drawing reduction. So, this is our true stress strain plot. So, this is stress, this is strain. Now, if we draw just the flow behavior, which is the plastic component, the plastic deformation behavior, it will come out like this. So, this is what? This is sigma equal to, or the effective stress equal to k epsilon to the power n. Now, if we plot our drawing stress onto this sigma d, how would it look like? It will look like this. So, this plot is and what is the assumption here? If you see, we have not put 1 over eta at this point, which means we have said that eta is equal to 1.0. And this epsilon star is the critical strain up to which we can go, and what is this? It is this strain. What if we have the efficiency of the system little lower than this? Then it will, the plot will look something like this. So, this is our sigma d. To differentiate it, let me put a prime over here, and we have 1 over eta. So, you can see it is 1 divided by a factor less than 1. So, sigma d is always higher for a given strain. So, this sigma d prime is always higher than this sigma d. And again, to differentiate from this epsilon star, which is the critical, I will put a prime over here. So, this is our epsilon star prime. So, all the things that we discussed using equation can now be also seen through this plot. This is our stress strain plot, this is the actual sigma d, and our sigma d, this is the flow behavior sigma, which is given by the power law behavior, and one of these plots are our drawing stress behavior. So, you see that our strain should always be such that sigma d is below this value. So, if we had a efficiency of 1 in the system, then all the way up to this point the sigma d value is lower than the flow stress sigma, or even if we have efficiency less than 1, then we have another plot, and up to this strain value the sigma d prime remains below sigma bar. So, that is what we want. The point at which it crosses is the critical strain we should never cross, and therefore, these define your critical strain, the maximum pass or the maximum drawing that is possible in one pass. And we also said that if you need more reduction than that, what is the way out? You will have to have multiple passes. So, that makes the picture clear of what or how we get to this critical stress and the critical strain value for drawing operation. Now that we have seen it, let us try to solve a simple problem based on this, and the problem is what is maximum strain for a material which shows ideal plastic behavior. What is ideal plastic? Ideal plastic is when n is equal to 0. That is, if you were to draw the stress strain plot, true stress strain plot for the flow behavior part it will remain constant. So, this is sigma bar epsilon bar. So, the material flow stress value remains constant no matter what is the strain, and that is called the ideal plastic. The question is, what will be the maximum strain for this kind of ideal plastic when you are doing a wire drawing operation. So, all we need to do is put in the values in our equation. We know that epsilon star is equal to eta 1 plus n, but n is equal to 0. Therefore, epsilon star is equal to eta times, or just eta, because n is equal to 0. So, it is just eta, and that means that if you have efficiency of 65%, which is more or less that you would get in industry, then epsilon star would also be equal to 0.65. So, this is the maximum strain that you can get, and for a system where eta is equal to 1, you would get epsilon star equal to 1. Now, you remember that epsilon is also equal to, or in terms of area reduction, we can put it like this: ln 1 over 1 minus r. We went through the individual steps to show that epsilon is actually equal to ln 1 over 1 minus r. So, if we know that epsilon star is equal to 1, we can inversely calculate what is the area reduction, and you would get area reduction of 0.63, which means in percentage 63% area reduction. So, this is the maximum that you can get for an ideal plastic and assuming a very efficient system. If your system was not efficient, let us say if the system efficiency was 65%, then this value would also reduce. So, you will get something like 50 or 48% depending on. So, for example, eta 0.65, you can see the calculation or try it on your own for eta equal to 0.65, and assuming that your so your strain would come out to be 0.65, and in that case, I just assuming ideal plastic, you would get percentage reduction approximately equal to 48. So, this is the maximum area reduction that you will get for a material which is ideal plastic and for which the efficiency is equal to 65%. So, this is example for this, and here also you can see that if you want more than 48% area reduction, you will have to do more than one pass. Now, let us get to another still interesting aspect of wire drawing. Again, let me just draw a rough sketch of the wire drawing operation. So, this is how this is the die, this is where your wire comes in, and this is where your wire goes out. Now, you remember we said that you are able to put a stress in a thinner region and still able to do deformation on a thicker region, because this is work hardened. Now, what if you, like we said, at some point your wire has broken for whatever reason? It could be because there was some defect, not particularly because of your fault, it has broken. So, now what you need to do is, let us say it has broken from somewhere over here. Now, what you need to do is, to begin the process, you will have to shave off some material so that you can start pulling it from the other end. Now, if you just start, or if you just shave off the material, to pull out, what will be the problem? Can you do this? What will happen is that this part will not really be work hardened anymore, and so you are trying to pull by applying stress on a thinner region with same yield stress, and you are expecting or hoping that a material with the same yield stress, but with thicker diameter will start to deform, which is not possible. So, you need to, the solution is that you need to work harden this part of the region some other way around. You cannot do the wire drawing because you need to insert through this die at some point, and since the wire is broken from somewhere over here, you cannot insert it or pull it out from here. So, you need to work harden this initial portion by some method. Now, that is the solution, but how do we achieve that? We cannot apply, like I said, wire drawing operation. What can you do? This operation is called swedging. So, basically every time your wire breaks down, you will have to add an additional step, which is of swedging, which is another way to look at why, if you are running an industry, you will not want your wire to break down, because then this involves delaying the process and less productivity. But anyhow, at some point it may break, and in that case you will have to do this work hardening. How it is done? So, it is the swedging is a process like this. Let us say this is the final diameter that you want. It will have a hammer kind of structure. So, these are 4 hammers which can move in and out like this, and there is a 4th one over here. So, what makes them go in and out? There are spherical balls all around. So, these spherical balls are still inside another cylindrical structure. Now, what is done is that this whole part is rotated, which means these spherical balls will at some point come and press this hammer onto this wire, or you can put a wire over here, or you can put a diameter or rod over here. So, let us say that initially your rod was of this diameter. Now, when it starts to rotate, every time a ball comes over here, it will push this hammer inside, and it will kind of hammer this wire at this point and keep rotating. So, this whole thing is also rotating at the same time. And also the spheres are rotating, which ensure that this hammer operation is carried out. So, this hammer operation gets carried out, and this part gets hammered, and eventually it will get beaten into this thinner diameter. So, in the end you will get a wire of this diameter, and you can keep pulling or pushing through this, so that you get sufficient length of wire with this kind of diameter. So, this is called the swedging. So, the purpose of swedging is to work harden the initial part of the wire. So that it can be drawn or pulled. Okay, so that is all we have about this uniform energy method or the lower bound method, where we discussed in some amount of detail extrusion method and the wire drawing processes. We also looked at the maximum reduction that you can get in wire drawing. We also saw that you can relate the extrusion pressure or the drawing stresses to the actual work, which, and if you are assuming that the actual work is equal to the ideal work, which is when no friction is present or no reduction is or no redundant reduction is being carried out. In that case, this extrusion pressure would also be equal to the ideal work, and so we get a very nice relation or nice way to calculate extrusion pressure or the drawing stresses. And we also saw that under this condition of ideal stresses or ideal work, your drawing stress required to reduce the diameter is less than the same deformation or the same reduction that you can get in tensile stresses. So, that is that covers most of the important or fundamental aspects using the uniform energy method or the lower bound method. You can extend this to any other kind of operation. You just need to calculate the integral sigma bar d epsilon, which is ideally what is the real work that is going on. So, that is the ideal work, and then you can relate it to some of the external parameters assuming no friction. Now, we will go to another method as we promised earlier, which is our upper bound. So, now we have seen at the lower bound, which is the minimum amount of force or pressure that is required. Now, we will go and try to calculate pressure or forces calculated which will form the upper limit. That is, in reality you cannot or you need not go beyond that pressure or force. So, our next step is upper bound analysis. Now, what is upper bound analysis, or how do we obtain upper bound analysis? In upper bound analysis, what we do is we assume a particular deformation field, which is as long as it is self consistent and follows some assumptions, we will look at that, and then we calculate what will be the internal work rate in that deformation field and calculate what will be the external force or power or stress requirement for that. And now we equate these two, the internal deformation rate and the external work rate. We equate these two, and from this we are able to obtain pressure or some stress value which we can calculate or which we can relate to the, or which will basically form the, give us the upper value for this kind of operation. So, this is a estimate of the collapse. Collapse meaning deformation. We are not, we do not mean failure. We mean just when you are doing the deformation at some region somewhere shear is taking place, we are calling that just as the collapse. So, estimate of the collapse of structure made by equating the internal rate of energy dissipation to external rate of work. To rate at which external forces do the work. When we are using this analysis, we are assuming certain, we are taking certain assumptions. So, it is important to first look at some of those assumptions before we can proceed and start to formulate the equations. So, what are those assumptions? Some of those assumptions are straightforward. For example, we are assuming isotropic behavior, meaning we are saying that the material must behave similar in all directions. So, these are the assumptions. work material is isotropic, and you would see why we will be able to justify the use of this assumption when we start formulating or trying to get formal equations for this. Isotropic and homogeneous. So, not only isotropic, but also homogeneous, meaning one part of the material does not behave differently from the other part. So, this is assumption number 1. Another important assumption is that of frictionless. Frictionless may not be the real situation. So, but we also have frictionless and or not and but or constant shear condition at interface, basically work tool interface. So, for example, if we are doing the wire drawing operation, the tool would be your die and the workpiece would be the material which is deformed. So, this is assumption number 2, and another very important assumption is that outside the deformation zone, we assume that the material is hard, or basically it does not deform, or basically it is rigid. Material is rigid. So, there is no scope to assume that there will be graded behavior of the material, that is less deformation from very sharp or high deformation to small deformation to even smaller deformation and to the region that there is no deformation, which you may say is the true behavior in most of the deformation processes, but you would see that we are still able to get a good upper bound estimate for most of the processes. In this we are saying that all the deformation is limited to that particular deformation zone or that particular shear plane that we will say is the deformation zone, but beyond that it is not deforming. So, these are the assumptions that we have, and based on this assumption we can now come to what is the actual step involved. I am going step by step here to make sure that you can come back and see those things, to see what are the different steps in formulating the equation over here. Now, next is what is the method or steps. These will become very clear once we start solving some of the problems. The method involves that we have to have an internal flow field is to be assumed. So, it is giving you a lot of leeway. You can define your own internal flow field or the deformation, what kind of which particular way the deformation is taking place. An internal flow field is to be assumed, and of course, it has to be consistent. And with example, when we come to example, I would show what exactly do we mean by consistent. What we just to put it in words, to say consistent, it means that you cannot assume that after deformation material is remaining inside the deformation zone. At some point the material, if it keeps moving after deformation, it must come out and so on. Some of these things when you put together, you can say these make it consistent behavior. Second is that you have to calculate energy consumed in this deformation field. So, you have made a deformation field which is consistent, then you have to calculate the energy consumed in deformation field. using material behavior, material properties. So, for example, material properties would be like the shear strength or the yield strength. So, this part, when you are calculating the energy consumed or the actually the energy rate consumed, you are putting or utilizing only the material properties or all the properties that exist for the material, and based on that you are saying this is the energy consumed for the deformation. Then you calculate rate of external work, and for that you utilize the area on which this forces are working, the velocity at which the parts are moving. So, here you utilize the external information. For the internal rate of work, you utilize internal or inherent properties like the material properties. For the rate of external work, you utilize external parameters like area on which the forces or shear stresses are acting, the velocity with which the parts are moving, and so on. And the last part is to equate rate So, in these 4 steps you would be able to get a equation, and from that equation you will be able to obtain a relation for pressure or stresses in terms of property parameters and mostly the velocities. And to leave you with something to think about, I will draw a simple condition or a simple deformation field and give you some hint on how to approach it. So, let us say we have, this is something which true for operation like machining. In machining also you are doing, although you are shaving off the material, you are taking off the material, but there is also some deformation taking place, particularly the chips that come out. So, let us say this is the part that is being shaved off and this is the chip that is coming out. So, this is SS prime . So, let us say this part moves on, and from over here it gets on to a deformed zone like this. So, A B C D has converted to A prime, B prime, C prime and D prime. The velocity here was V1, the velocity here is V2, and what we will need is to relate this velocity, and you will get another additional velocity. To begin with, I would ask you to draw a vector diagram on how these velocities are changing, and what will be the third velocity vector that you get here. How can you relate it with the deformation field? The deformation field, as you can see, is related, is somewhere contained over here. So, you give a thought onto this, and we will come back to this point in the next class. Thank you.